Hello everyone and welcome to this week's Seds Online webinar. We're really pleased to welcome Joris Eggenhuisen from Utrecht University. Joris completed his PhD at the University of Leeds in 2009 and then went on to a position as a postdoctoral research fellow at Leeds University. Later in 2009, Joris became the assistant professor in sedimentary geology in the Department of Earth Science at Utrecht University and has held this role since then. In 2011, he became the scientific director of the Eurotank Flume laboratory at Utrecht University and has been leading the Eurotank research team since then also. In his research, Joris investigates the transport and deposition of sediment by water in deep water settings through physical experiments. And today, Joris is going to talk to you about some of this research in his presentation on deep water sediment deposition from hybrid contour-turbidity currents. So without further ado, I'll hand over to you, Joris.
Thank you, Catherine, for that introduction, and thank you to Seds Online for giving me the opportunity to talk to you today about our research. Oops. So I want to start by emphasizing the role of my co-authors, Elda Miramontes, Florian Pohl, Ricardo, Silva, Jacinto, Giovanni Poneti, and Javier Hernández-Molina. We're all at different institutes, and this was really a team effort of people from different institutes coming together. And we all have colleagues and co-workers at all of our institutes, which we are heavily indebted to, but there are too many of those to name here today, but know how important you are for us. And secondly, I would like to acknowledge that the funding for the specific experiments that I'm going to be showing to you today was supplied by the joint industry consortium of the Drifters Research Group based at Royal Holloway, University of London. And you can see the logos of the companies that supplied the funding at the bottom of this title slide. So I'd like to take you today along on my journey of changing my perspective of what a deep marine depositional system is. My old perspective used to be really the turbidity current paradigm, which is turbidity currents are really strong, powerful, sediment is in suspension, vigorous sediment transport, and gravity pulls this mixture straight down the slope. And here is an example of a video of a turbidity current that does this. It goes straight down this slope in an experimental setup, and we can measure its velocity with the velocity probes that are on the beam that you can see in the video. And we measure this velocity profile, and the turbidity current is traveling at about 1 meter per second into the basin, about 0.9 meters per second. And my entire research for well over a decade used to be focused on just this idea and this problem and all of the challenges that are associated with it. Turbidity currents go straight down the slope. Well, we do allow for the eventuality of a sinuous channel. And we know that there are many sinuous channels in deep water environments. And yes, in that case, of course, the turbidity current follows the sinuosity, the orientation of the channel. And here is a nice seismic example of the Atlantic coast of Africa in the paper by Michael Janocko and co-authors, published in 2013. But even then, you can see in Michael's interpretation that yes, okay, the flow goes around this sinuous channel thread, but by and large, the flow direction really is dominated by the orientation of the channel belt going straight down the slope. So always down. And then when the turbidity currents get to the bottom of the slope and they go onto the basin floor, they form these amazing features of the natural world, which we call submarine fans. And here's an example by the work of Deptuk et al. From the Golo Basin. There's a map on the right of this slide. So the Golo Basin is a very well-known, well-studied basin between Corsica and the Italian mainland. And we can see in black a number of threads of canyons coming off the Corsica shelf, supplying turbidity currents and their sediment to the basin floor fans in the basin. We can see a seismic section through one of these fans. And our community has done a fantastic job of really documenting in great detail the internal architecture of these fans, showing that they are composed of different subunits that are often stacked laterally, and these are themselves composed often of different subunits which are thought to be dominantly stacked on top of each other. And then there's another level of complexity underneath that where we get to the individual beds from each turbidity current depositing a turbidite onto that fan. So an incredible body of knowledge has been built on these features from the turbidite, the turbidity current paradigm. And I have always been, and I am still, an enthusiastic member of that community, making progress on questions relating to these features. But my perspective on what deep marine depositional systems are has really changed in the past years. And a pivotal meeting for me was this conference organized at the Geological Society of London in 2017, January 2017. The title of the conference was Deep Water Depositional Systems, Advances and Applications. And it turned out that the meeting wasn't about deep water depositional systems really in a broad sense. It was dominated by people thinking and talking and presenting from the gravity current, the turbidity current, the mass flow paradigm. Sediment goes down the slope into the basin. And only very few presentations in the conference really took a different perspective and a broader perspective on what deep marine depositional systems are. And two of these were given by Elda Miramontes and Javier Hernández-Molina respectively, and really made me think. And I'm really happy that the chats and conversations and discussions that we started up after their presentations eventually led to the collaboration between people with different perspectives that I'm presenting to you today. So Elda also, she presented some data that she published in her 2016 paper, also on the Golo Basin that I'd read many papers about from the turbidite research community. And it blew my mind. I had never thought about this. I'd never thought about what the context of the turbidite fans in the Golo Basin is. And it turns out that the context of the Golo turbidite fans is the contourite systems. And Elda documented how the contourite flows associated with the Levantine intermediate water, which is on its contorted way towards the Straits of Gibraltar, actually deposits contourite drifts that constrain, that fix in place the Golo fans that I've read so much about. And none of those papers mentioned any of that as far as I knew. And it actually turns out that these drift deposits form the underlying strata that are actually interspersed in between the different fan units of the Golo fans. So the contourite system associated with the flow in the Golo Basin on the Mediterranean water body scale is actually the dominant setting process of the largest scale of the Golo turbidite fans. And for this presentation, I took Elda's seismic cross-section of the drift deposits, and I rescaled Deptuk et al.'s seismic section of a submarine fan, and it's right there. And it's tiny, and it's almost insignificant. It forms this tiny sliver of sandy turbidite fans in between this really big contourite drift system, the toe of this contourite drift system. And this really made me question my own perspective. So I very much enjoy, and it's been very beneficial for me in the community to really focus on the turbidites in deep water, but I felt a little bit like these racing horses that have blinders on the side of their eyes to make them focus and really stay with their attention on a single subject, which can be great. But the risk of it is that you lose sense of your environment, and you're not looking around broadly enough, and you miss the important context of the system you're interested in. So it made me take a step back and actually look broader at deep marine systems. And many people have been doing the same over recent years, and there's a much more balanced perspective of deep water depositional systems that is now clearly emerging in literature. And it is that of really taking an integrated perspective on mixed bottom current, turbidity current systems. And these are the concepts conceptualized in the Fonesu et al.'s paper that came out last year, but has a 2020 date, of passive systems where where contourite and turbidity current systems form each other's template, each other's substrate, but don't really have much interaction beyond that. And then there's a step where there's a phased system, so there might be a system where the turbidity currents are really dominant, but then when the turbidity currents are not dominant, the bottom currents start reworking the sediment in these types of systems. And then there are synchronous systems where both turbidity currents and bottom currents are active at the same time. This categorization in the different types of mixed system kind of started with older literature going back to roughly the 1990s. So there is early work on mixed systems like this, and a very famous graphic from the Shanmugam's paper published in 1993. It's a sedimentological model based on Gulf of Mexico deposits. And we can see here that turbidity current travels down a channel axis, and there is some overspill over both levees, but it's suggested in the drawing that there's actually more overspill on one of the levees, and this levee is a little bit higher. And then there's a plume of sediment that rises up vertically from the turbidity current, and when it reaches a kind of ceiling, it starts to be entering the bottom current, and it's taken away like a type of thunderstorm cloud or volcanic eruption that you sometimes see. So this is the concept, the sedimentological model that was built for a system like this in 1993. So more recent documentations have made abundant use of seismic cross-sections. And this is a seismic cross-section from the Pearl River Basin in the South China Sea. And the bottom current in this image is going from, in the left image is going from left to right over the top of these canyons, which are up to 400 meter deep and a couple of kilometers wide. And you can see that these channels have cycles of infill and reincision, infill and reincision, infill and reincision. And between each of these cycles, the position of the canyon shifts a little bit. And this creates a stacked depositional pattern, and the stacking direction, so the stacking offset, is consistently with the direction of the bottom current in this particular system. And that has been interpreted in later papers by the same authors as an effect that's drawn in the panels on the right, where we can see that there's a contour current going over the top of a turbidity current, and this creates Kevin-Helmholtz billows and bores on that interface that actually break onto the steep downflow channel margin, and that creates erosion there, and that is then thought to result in this pattern of unilateral channel migration in these canyon systems. Strikingly, the exactly opposite migration pattern has also been reported, especially for the systems that are now well documented in the Tanzania and Mozambique offshore regions. And this is from the paper by Fonesu et al. Again. We can see in the seismic data in the cross section, again, the bottom current comes from left to the right. And here the channel deposits are stacked towards the bottom current. So the channel migration direction, the stacking direction, is actually reversed with respect to the system we looked at in the previous slide. And again, there's a sedimentological model for that documents how the bottom current is going from left to right in the green arrow. In yellow, there's a turbidity current coming down a channel, which creates a dense flow, and then the bottom current somehow extracts from this what's called a dilute flow, which then flows up onto this lateral drift and to deposit sediment on that side of the channel. And that's then thought to drive the channel migration of this particular system. So many more of these sedimentological models, so I call this sedimentological models, so they are models that are built on robust observations of the sediments and the stratigraphy. And that's a very robust part of this type of work often. But then they construct sedimentological models also about the flow interaction and the flow process. And all of these models are different. And there's a wild variety really of flow interactions and patterns and circulations. And the only thing that really is the same in all of these models is the enthusiastic use of arrows to indicate hypothetical flow patterns. And that's really interesting to me because none of these flow patterns have been measured in any of these studies. And that's awesome because this means that this is the perfect research theme to start doing some process modeling and to start doing some experiments and say, okay, let's do some experiments. So let's try to measure some of these things. So what happens when a turbidity current and a contour current are active at the same time? And that was the starting point of the experiments that we did last year and that we are presenting to you today. So the purpose of the experiments is very, very simple. It is to obtain the first physical measurements of a combined flow field of a contour current interacting with a turbidity current in a synchronous system. So just that. That's what we wanted to achieve, and to look at the depositional pattern in those experiments. So the setup we use for it is the Eurotank basin setup that we have in Utrecht. Schematic drawing on the bottom right of the experiment, the setup for this experiment. And on the top right, you can see an image which gives you a sense of scale. There are two of my co-authors here are flattening the basin floor. So this light colored area you can see, that's the sand on the basin floor. So it's just this horizontal part covering about half the setup. So we have about half the Eurotank in the field of view in this picture. It gives you a sense of the scale of the setup. So the first thing we needed to accomplish in the setup is a credible and stable contour current generation. And to the best of my knowledge, this hadn't really been done before. And the idea we decided to use and to pursue is what I call here the flywheel principle. So a flywheel is used in mechanics to store a relatively large amount of rotational kinematic energy within a stationary device. So what you have is you have a big wheel with a lot of mass, typically made of metal at its outer rim, and you set it to rotate on a bearing with very low friction. And once you've got it going, you need to input very, very little energy to actually keep it going, because the only energy you need to put in is the energy lost in friction in the bearing. So you can have you can maintain a high rotational energy with the input of very, very little energy. And we decided to do this in our Flume tank as well. So we set up a really big rotating vortex in the entire basin, by putting in a relatively modest amount of energy with pumps on the side. And these pumps, there's an image on the top left here where we can see pipes coming in and pipes going out of the flume on the top. And each of these pipe pairs pumps water out of the vortex, and then on the other side it pumps water back into the vortex with the same direction. And this is the only thing we need to do to keep the entire basin in a very stable rotating vortex with a lot of rotational energy. So we turn the entire Eurotank basin into a big vortex flywheel. We have 3 intensities and we of the contour current, and we achieved that by simply buying 3 pumps. So we can turn 1 pump on, 2 pumps on, or 3 pumps on. Very easy regulation mechanism. So the turbidity current generation, we decided to not be novel and not be creative. So we actually decided to use exactly the type of turbidity current boundary condition that we've been using in the Eurotank for roughly the past decade in a number of studies that we've published. And you can use other types of experimental turbidity currents, but this gave us a solid footing. At least we knew what was going to happen if it was just a turbidity current. And we had a kind of sense of security, something to hold on to. So we stuck to that established recipe. Slope is 11 degrees. This is exaggerated. It's a scaled slope. And in small scale models, often with gravity flow and rivers, the local slope is actually exaggerated with respect to large scale natural systems. And the channel is 80 centimeters wide and 3 centimeters deep. That's the channel size that Jan developed for his 2018 paper. And we use a mixture of fine-grained sand, sediment concentration of 17%, discharge of about 8 liters per second, and a total volume of almost 1 cubic meter of the turbidity current. So a final bit of development for the setup was needed for measuring the velocity. And if you've seen turbidity current experiment data being reported, you have probably seen velocity profiles, such as the one on the left here, which I also showed earlier. A velocity profile of the velocity of the turbidity current plotted above the height of the bed in the channel axis in this case. And what you might not realize if you've never done this work yourself is that that's not actually the velocity that the probe measures. This type of UVP probe only measures the velocity component in 1D in the direction of the probe itself. And we actually need to assume that the turbidity current goes straight down the slope parallel to the bed. And in our old frame of mind, in the turbidity current paradigm, this is fine. We can live with that. We know it's true. We can measure it and check it. And, we know that it's an approximation, but it's an approximation that creates only an error of 2 or 3 or 4% at maximum in our velocity profile. So we're happy with that. But of course, in these experiments, we put the entire objective in reconstructing an a priori unknown 3-dimensional flow field. And in that setting, this old-fashioned way of working with UVP probes is entirely not usable. All the basic assumptions you have to make are invalid. And it turns out that actually UVPs are not very useful in isolation. Also not if you start working with many UVPs pointing at each other, which is really complicated to do and won't solve your elementary problem in this case. So what we actually did is get a new Doppler machine, at least for our laboratory, to measure 3-dimensional Doppler velocities. And the way this system works, on the right you see a photo of it. There's a probe holder, is a disc. It is partially obstructed by the beam that is holding the disc here. And this disc has 4 probes. One is vertical, it's a central probe, and it has 3 side probes looking at angled towards the center of the measurement location. And in the middle here, I have sketched the central probe and 2 out of the 3 side probes, just so that I didn't have to make a 3-dimensional sketch. And the central probe emits an ultrasound burst at 2 megahertz, in this case, vertically downwards, and that ultrasound meets sediment, and part of the ultrasound is reflected back upwards in all 3 directions of the 3 probes. And that sound is then recorded by the 3 probes. So it's sound coming of the same sediment particles is recorded at the same time by the 3 probes. And the principle that this measurement technique uses is the Doppler effect. And we all know the Doppler effect from when there's a siren, for instance, a fire truck or an ambulance coming down our street. When the vehicle is approaching us, the velocity of the vehicle is directed towards us, and that means that in space, the sound waves are actually compressed together when they reach us, and therefore they have a higher frequency, a higher pitch, and we hear a higher sound. And then when the vehicle passes us and it drives away from us, the reverse happens. So actually the sound waves are extended, they are stretched in space by the emitting vehicle. And when they reach us, they have a longer wavelength, a lower frequency, a lower pitch, and we hear a lower sound. And these probes use the very same principle. So suppose that these sediment grains that I've drawn here are moving to the right. It means that the sound being reflected to the right side probe has got a slightly higher pitch, and the sound reflected to the left side probe has got a slightly lower pitch. And the probes are really geared to figuring out what this change in the pitch of the sound is. And from the 3-dimensionality of the 3 probes, you can actually calculate the 3-dimensional velocity vector of the sediment particles that reflect the sound. And this is really what gets me very enthusiastic. It's a fantastic piece of technique that we used for the first time in our lab in these experiments that I'm showing here today. So results then obtained with the probe. This is just the contour current before the turbidity current arrives, and we can see that the along slope, so the contour current velocity, is 0.1 meter per second, 0.14 meter per second, and 0.19 meter per second, the 3 intensities that we've set up. And the downslope velocity of the contour current is almost 0, far above the bed, and then at the bed there's a small downslope component as well. That's probably because of the 3-dimensional shape of the channel that the contour current is flowing through. But this is small compared to the gravity current, the turbidity current downslope velocities that we will see. So here is the video of the reference run at the top, so no turbidity current, run A, and then at the bottom we have the turbidity current with intermediate in contour current flow velocity. What we can see is that the turbidity current spreads out symmetrically over the slope and has vigorous overspill on both sides. But when there is a contour current, the margin of the channel from which the contour current is coming has no overspill. The overspill is blocked entirely on that side. And there's a very, very sharp position, a lateral front that really stays in one position at the channel margin. There's no sediment being suspended over that margin at all. That's a contradiction of the sedimentological model published in 1993 by Shanmugam. And then when that sediment is entrained in the contour current from the turbidity current, it starts to mix with the contour current, and then it's on its way out of the channel to be incorporated into the contourite drift system along the rest of the margin that can be on that part of the marine basin. Okay, I mentioned all of these aspects looking at the video. So the velocity measurement results then. I first plotted just a conventional perspective, only the down slope velocity component here for the 4 experiments. So the reference run, 0 meters per second contour currents, and then 3 intensities of contour currents. And what is striking is that when there are intermediate contour currents in our setting, the downslope velocity of the turbidity current actually increases. And then when we have the highest contour current velocity, the turbidity current velocity actually decreases. And this pattern is reflected very, very strongly in the depositional pattern that we measured with a laser scanner after the experiment. So in panel A, we see the depositional pattern of the reference run. So this is very typical for our turbidity current experiments in this setup. There's some channel thalweg sedimentation, levees forming, and then a big lobe on the basin floor. And at intermediate contour current intensities, actually the channel sedimentation is suppressed. It's greatly reduced, and that's associated with these larger velocities of the turbidity current. And then when the contour current velocity really increases, the reverse actually happens, and there's a lot of slope sedimentation associated with the channel, especially at the lower slope. That was a very unexpected result. If we actually plot the along slope velocities, we get a slightly more expected result, perhaps, if you look at the big picture, which is that at the very top of the measurement, the along slope velocities are approximately equal to the contour current velocities, so really far above the turbidity current. The contour current velocity field simply dominates. But what we can see is actually that the along slope velocity inside what we would normally call the turbidity current is actually significantly large above 0, really far down, all the way down to the base of the bed. Some people think they see here actually a reverse velocity going against the contour current direction at the base of the intermediate intensity, but we haven't reproduced this measurement, and I would want to see a reproduction of this before I claim that that's actually a solid observation. So we can plot that flow current profile in a different way as well by looking at the deflection of the flow. So the horizontal axis is now the degrees of deflection of the flow from the turbidity current direction. And what we see is that, again, the deflection starts to take place all the way almost at the bed of the flow. So the turbidity current velocity field is pervasively changed by the action of the contour current acting over flowing over the top of it. So looking at channel cross sections, the lateral front really prevented levee overspill on one side of the channel, and that means that there's no slope aggradation on that side of the channel, only a very small diminished levee developing, and this is really outperformed by a lot of sedimentation on the other side of the channel, on the downflow side of the channel. And it means that the channel actually shifts towards that position of the lateral front. And in this way, we find that our stratigraphic observation, the depositional observation of the channel cross-section, are consistent with the channel stacking against the bottom current direction that was documented in the Tanzania, Mozambique offshore systems. So a very important and obvious question to ask is, how do these experimental results translate to the real world? So how does this scale to natural contour currents and natural turbidity currents? And many of us would ask this question. I would have asked this question with some skepticism 2 years ago, saying, yeah, but turbidity currents are so powerful, they go straight down the slope, gravity is so strong. You know, are these contour currents really strong enough in natural systems to have the effects that you have measured in the experiments? And to that I would say, well, my new perspective is that deep seas are actually not static environments at all, but rather dynamic environments. I'm really big fan of these videos that institutes like the Monterey Bay Aquarium Research Institute are putting on YouTube. This one has a different theme. It's about trash in deep sea systems, but it actually serves as a really nice illustration of the level of dynamic conditions in canyons and in channels, because this plastic bag through which somebody has expressed their love for us by throwing it in a river or in the beach, it ends up on a canyon floor, and you can see it as a tracer of the canyon flow, and it transits the stream at a velocity of about a decimeter or so a second. That's quite qualitative, of course. I'm really glad that a couple of weeks ago this fantastic data came out, measured in the Argentina-Uruguay system. And they actually went out with ADCPs to measure the flow velocity in a grid across this entire system at 10-kilometer spacing. And the flow velocities above the bed are indicated in colors and with the length of the arrows. And the yellow colors are velocities, average velocities of 20 to 30 centimeters per second. Greens are a bit more rare, 10 to 20 centimeter, and orange, 30 to 40 centimeters. And then there are rare velocities lower than 10 centimeters and rare velocities up to half a meter per second. So these are really, really dynamic environments, also when there is not a turbidity current. And this is something where I know that many turbidity current researchers are listening to me now, that this is really an important message. Deep sea depositional systems are dynamic, and many things happen even if there are no turbidity currents. And that is something that I'm really becoming passionate about and really recognizing how important that is. So we argue that we need to scale our experimental results about the interaction between the contour currents and the turbidity current by the ratio of the two current speeds. So what that means for our results is that you can see underneath the velocity profile with the blue arrows, I've indicated the speed range of our contour currents, 10 to 19 centimeters per second. And then in red, the velocity, the speed range of the downslope component, so 76 to 96 centimeters per second. So the speed ratio of the two dominant currents here is 10 to 25% in our experiments. And this is the ratio we should use to translate our results of the impact of the contour current system to the real world. And what that means is that intermediate to fast contour currents of a few decimeters per second will have the interactions that we see in our experiments at turbidity current flow velocities of 2 to 3 meters per second. Most turbidity current velocities are going to be in that range. Yes, there's a huge spread. Some are faster. They are the biggest ones. More than 10 meters per second, I think, is very, very rare. You're looking at a once in a century to even longer events. And most turbidity currents we know of now are 1 to a couple meter per second. And many are even slower than 1 meter per second. And this is documented quite nicely, or graphically illustrated quite nicely in this graph by Arne Furman's paper that came out last month, I think, in Geology, where they plot observed and measured velocities from turbidity currents in red with kind of generalized bottom current velocities. And many of us would have thought before that the turbidity currents are much more powerful, they dominate, they don't care about bottom currents. But actually, if you look at it this way, bottom currents are present when turbidity currents hit really quite often in this speed ratio range of 10 to 25% of the turbidity current. And I'm quite happy to argue forcefully that the interactions we see in our experiments are likely to be representative of many, many turbidity currents in natural systems. So I'm happy to be forceful about that, but of course we did 4 experiments, one of which was a turbidity current experiment, and in 3 we had one type of contour current set up. So we have to be positive in our outlook, happy with these results, but it also serves as a realization that there's many, many themes to address that we need to take much better care of still in literature. So there's lots of things to do. And I'd like to highlight these themes at the end of my presentation here. And the first is that Mulder et al. In 2008 kind of wrote the basic division of mixed systems into passive, phased, and synchronous systems. And I'm afraid to say that the literature since then has only become more confused. And I think it's because there very little diagnostics have been established. So people keep observing new examples in a new system and then saying, oh, I interpret this as a synchronous system or this as a such system and so system. But there's not a set of diagnostics that we can apply to these systems. And I think that that's because there's a lack of process modeling, supplying really a physical understanding of what goes on in these 3 different types of mixed systems. So this is a really important theme: the timing of activity and the strength of the flow systems. Another really important theme that is very confused in the present literature is to differentiate the morphologies and to figure out how these different flows actually flow through completely different types of morphologies. Because at the moment, it seems that there is an atmosphere of discussion between people who have worked on completely different types of deep water systems. Here on the left, I would, and this is my own qualification, I would say these are confined, narrow upper slope canyons, or perhaps even upper slope gullies, that have multiple sources, almost a line source from a shelf. And I think that that's a completely different system to look at and to discuss than the system from Tanzania and Mozambique, which is a relatively point source, very focused source of sediment coming at the base of a supply from the shelf, and a relatively more open morphology where the currents are more open to attack from the contour currents going past. And there's a lot of confusion about what the morphological setting of the different examples are in the literature at the moment. And I think that's something that process modeling can help address. And finally, we only looked at contour currents in our experiment here. But if you actually look at the bottom current literature, contour currents are really only one type of bottom current. And there's a huge diversity of saline outflows over sills, deep marine tides being amplified in canyons, internal waves, dense water cascades in systems like high altitude systems like Antarctica, eddies and vortices that have a completely different structure from the contour currents that we modeled that simply go straight and with one velocity. Things called deep sea storms, which I don't think I understand what they are yet. Cyclonic waves, pycnoclines, which in themselves aren't really a flow structure, but tend to emphasize and concentrate all those other currents. So there's a huge diversity of topics still to address in how turbidity currents interact with that. I said finally, but actually there was one word that I had somehow failed to use in this entire seminar, which is really an elephant in the room of this discussion, the Coriolis. And what's going on with the Coriolis effect? it's quite well established, and we know very well that the Coriolis effect is a very important dynamic forcing of turbidity currents at high latitudes. But this is not included in the discussions about these systems at all. So here we see an experiment from Kosu and Wells, where there's actually a super elevated turbidity current going around a sinuous channel experiment, but the super elevation is actually towards the inner band. Now, I think as sedimentologists, we all understand how dramatic that is. So there's super elevation, but it's not towards the outer band, so the flow is not going up in the outer band. The super elevation is towards the inner band. And that's the dramatic effect, the dominant effect that the Coriolis force can have internally in a turbidity current. And how this compares to the external forces of the entrainment of the bottom currents that we look at in our studies is, as far as I now know, completely untreated in the literature. And I think that's a huge challenge. So I'll stop with my conclusion slide and just let this video run and conclude that I've become aware that deep sea environments are very, very dynamic, and deep water depositional systems are more than turbidites. And our experiments suggest that contour currents flowing at 10 to 25% of the turbidity current speed pervasively influence the flow field and depositional patterns in mixed contourite and turbidity current systems, and that this is the dominant way of actually introducing that sediment in the ocean system for its along margin transport. And with that, I'd be happy to take questions.
Thank you very much for that presentation. It was really, really excellent, and there's some fantastic videos in there as well, showing all the processes. It's fantastic. Okay. Thank you. Yeah. So the chat is now open for the questions. Whilst you're typing those questions, a few have already come through, but those who haven't had a chance to type them yet, while you're doing so, just to let you know that if you're watching this as a recording, please feel free to pop your questions into the forums, where there is a thread available for you to go ahead and continue this conversation there. And that way this is a resource for the future. So I'll go ahead and start reading out some of our questions from the chat then. Cool. So we have a question from Jaco saying, hi Joris, do you think there's a tendency to measure bottom current speeds in areas where they are expected to be high, just as there is a tendency to study modern turbidity currents in areas where they occur frequently? And therefore, is this approach representative of geological history?
Yeah, I think in any difficult measurement campaign, there's a risk that there's a bias that you go towards the places where the phenomena you're interested in matters the most. And that's certainly the case for the Argentina-Uruguay example that I showed. They justified a 10 by 10 kilometer grid with ADCP measurements over that entire terrace, because obviously they knew that it was going to be interesting to measure the contour currents there. So yes, that's true. But actually, if you look at maps of where contour currents are as important as in the Argentina-Uruguay system, and I just did that actually this morning because I felt this question was going to come. Actually, a significant part of the ocean margins, especially on the western margin of the oceans, has mapped as a similar intensity contour current system. And then also mind the review figure from Michele Ribesco's paper. That's only contour currents we're talking about. But if you add saline outflows, internal tides, waves on density interfaces hitting the system, actually those sorts of oceanographic processes happen everywhere. So I actually think that there's something important and interesting probably exists there in many systems. And that's answering the contour current part of your question, but actually you also asked about monitoring of turbidity currents. Yes, people go to the places where you expect them to be there, but actually the diversity is really increasing, and the more and more measurements I see, the published ones, but also the ones that I'm following that are as yet unpublished and going out, the diversity of turbidity current systems being measured is really expanding very, very rapidly. And the lesson I'm learning from that is that my old perspective of turbidity currents being big and strong and really high velocity, that's actually also a wrong bias, because many turbidity currents go at 80 centimeters per second, and then they are very thick, and then they transport a lot of silt, and in the bottom a little bit of sand. And that sort of turbidity current is going to be very, very easy to even wipe out entirely with a strong bottom current that goes at 30 centimeters per second. So I really think that we aren't even looking at the most extreme level of interaction in these experiments. And I'm really interested to seeing the range of measurements expand in both types of systems in the next few years.
Great, thanks for that. Our next comment is from Nick McCabe saying, a long time ago in the 1990s, Lionel Carter and I named fan drifts from the Hikurangi fan at the end of a greater than 1,000-kilometer channel feeding into the southwest Pacific Deep Western Boundary Current. Another is the Caicos Drift off the Bahamas.
Yeah, that's I wasn't aware of that specific paper, and I'm really happy of it being pointed out, because for me it's also been a journey of discovery of a new part of literature, because I've been so involved with siliciclastic, sand, turbidite deposition, that learning about these new areas of oceanography and ocean sedimentation is a really interesting journey of discovery. So I'm really happy with the comment. I wasn't aware of the paper, and I'm certainly gonna look it up, because it sounds like another example of just illustrating the enormous diversity of these types of systems that are out there. And that's something that I've really been interested to learn, is that in the broader theme of oceanography and ocean sedimentation, people are very comfortable with a huge amount of diversity of morphological settings and channel types. And I feel that from the part of the turbidite research that I myself was a part in, we have very much a tendency to put everything in quite a narrow framework and to try to generalize everything into concepts. But in ocean sedimentation, there's much more allowance for really the individuality of the diversity of all these systems and how special they all are. So I'm learning a lot about that. I'm certainly going to look that one up. Thanks for that.
Great. Our next question is from Mike Clare, saying, Joris, nice one. Biologists regularly record near seafloor currents for a range of purposes not related to sedimentology typically. How should we as sedimentologists better integrate with those studies?
Well, there has to be mutual benefit, right? Because they're doing it for their benefit. So I think we need to engage first of all, and then figure out where the benefit is. But I am aware that quite a lot of people already do this, but not much gets published. So I'm sure you yourself are actually thinking about this and have access to other measurement campaigns. But it's really about becoming multidisciplinary. And I myself have never really, if I'm brutally honest, I've always had quite a focused research missive, which has always been about the transport of sand to the basin floor in deep marine basins. But these sorts of topics that we're now addressing, we can't be really focused and self-centered anymore. We have to become interdisciplinary and look at the bigger picture. And yes, this includes biology, ecology, geochemistry, but still still have our own place in that in that landscape, of course. And I'm sure that's a challenge, but I'm interested in figuring out what my own role can be in that landscape in the next few years. If you have ideas, then we can chat about. I have some ideas.
Good stuff. The next question is from Dharma, asking, does the downslope distance travelled by the turbidity currents change with and without bottom currents?
Yes.
How does the sedimentation, how does the sedimentation loss due to bottom currents have implications on the downslope distance by the turbidity currents?
Yeah, I mean, when we, so 3 experiments, and people will tell this, so I'll point it out myself. So these are the first experiments, and obviously we need bigger projects to actually confirm that this happens. But the trend was so strong that I'm quite happy with the measurements as well, because I know the turbidity current behavior so well from the half a dozen other projects we've run in the setup. As soon as we turn the contour current on at this velocity, the transport distance of the sand increased. And we didn't sample it for grain size, but it sounds to me that it's consistent with the observation in natural systems, that the sand has got less mud and is coarser grained than people typically think in a only turbidity current system. So yes, the depot center goes further out into the basin, the flow velocities are larger, and you do this by somehow entraining the top of the turbidity current and moving it just in one way. And I don't fully understand that mechanism based on our measurement, and we really need to do better recording of the flow field and better sampling of the deposit to explain this. So initially, if you turn the contour current on, sediment goes faster and further into the basin, and then when the contour current becomes too fast, then you actually start to disperse and dilute the turbidity current, and then the deposition actually steps back on the slope. So there appears to be an optimum transport distance of sediment into the basin, which is when you have gentle or intermediate contour currents going over the top of the channel. It's very fascinating, and I don't have a full explanation of it yet.
Cool. Watch this space.
Yeah, I hope so.
Our next question is from Deborah Jeter, saying, hi Joris, thank you for the wonderful presentation. My question is, when we use grain size as a proxy for bottom water current strength, should we be mindful of influences of turbidity currents too? Can this lead us to somewhat incorrect conclusions of bottom current speed, or can the potential interference be ignored?
Yeah, that's a really good question, which relates to the sortable silt approach, I would think. And yes, turbidity currents are, I would say, a dominant source of that silt along the transport direction, along the slope. But I don't see that as a problem, because I think we can understand it very well how that happens. It just hasn't been described very well. But a few weeks ago, and this is literally, there's so much happening on these topics at the moment, a fantastic experimental paper was put as a preprint on Earth Archive, and I forgot the name of the first author. I apologize, but both Kyle Strom and Brian Romans were co-authors at Virginia Tech, so you will be able to find it on the Earth Archive preprint server, doing experiments to demonstrate that actually the turbidity current source of the silt, and then is actually a really good explanation, and they measured and modeled actually how that silt then gets sorted in the flow as it evacts that silt over the slope. So they actually supply a really strong physical justification of the sortable silt idea with their experiments. And it's something that, yes, I think it warrants more work. I was hesitant to pursue it myself because I felt that I didn't understand the physical justification of sortable silt. But now that I've seen this preprint from our colleagues at Virginia Tech, I think that there's an absolutely fantastic opportunity to directly look at the sorting of the silt away from the turbidity current in these sorts of experiments. And yeah, I'm really raring to go and try that out as soon as I can in Utrecht, really, because I have very optimistic about making progress on that.
Great. Our next question is from Arnud. Do you expect submarine lobe fan axes to be deflected by contour currents as well? If those sediment bodies or lobes or fans are more sandy in comparison to muddy levees than to a lesser degree?
Yeah, do I expect them to be offset or diverted? Pool. Well, yeah, I mean, the bottom current need to be active at the basin floor as well for that to happen, right? That's the first prerequisite. And actually, if I look at many of the basin models and 3D diagrams of these flow structures, actually the continental slope is the focus of bottom current activity. And I'm not aware of the studies. I would have to do the research myself. Very interesting question about whether the flow intensity on the basin floor is large enough to have any effect. I would say on intra-slope basins, so if we have an irregular slope, for instance, because there is a bottom current terrace halfway through the slope, and a lobe or a fan deposited on that intra-slope topography, yeah, for sure that could be deflected, but I have not thought about the dynamics of that yet.
Cool. Our next question is from Gillian, saying, excellent talk, Joris. However, I beg to disagree with you on the strength of turbidity currents in the geological record. The present day is not the key to the past for major sand-rich systems on passive margins. And she's glad that you made it clear that there is a large range of bottom currents and we're only just beginning to understand possibilities of present day in the past.
Sure, point taken, yeah. Yeah, that's a really good question. I don't know about that, Jill, to be honest, because I see a lot of deposits in channels that are, we call them high density turbidity current deposits. And that might be only the lower half a meter or so of the current. And on top of that, it might be dilute, fine-grained and silty clouds taking this the sand at the bottom of the flow only into the basin. So it's interesting to me that you suggest that you know what the flow conditions in the geological record were and that they were different than today. I'm pulling your leg a little bit. I see your point. There's a lot of ideas that we are in a high stand system and there aren't so many powerful turbidity currents at the moment. But to be honest, I think that the more and more we know about present day oceanography, the less and less I agree with that perspective. And there are plenty of systems around at the moment where you can go and look where there is a lot of turbidity current activity. Are they as strong as they were in the late glacial maximum at sea level low stand? Probably not, but what were the turbidity currents that deposited the famous Karoo fans in the Permian? Were they very fast? I wouldn't think you need very big turbidity currents to form that system. So that I think there's a huge variety also in deep geological time, and I think it's a bias which I'm challenging explicitly by disagreeing with you, even though I partially agree, and that turbidity currents are violent and strong, and that's how they formed all of these deposits. I no longer think that that's necessary. Also because I've seen tiny flows in the laboratory, also in free surface flows, that generate very dramatic erosive structures and massive beds in flows that go 1 meter per second and are only 10-20 centimeters deep. So I'm no longer so convinced that the deposits we see in the geological record are evidence of very dramatic flow conditions. So I'll just put that out there as an interesting discussion point. I'm also learning and trying to change my perspective, and I appreciate you putting out a contrary remark. I like that a lot.
maybe this is something to continue in the forums.
That would be great. Yeah.
Our next question says, excellent talk. Have you done analysis on grain size distribution from the experiments? And could you let us know what you found, if so?
Well, the answer is no, we haven't done that. And that was purely a constraint of the framework of the project, just bringing together these people from the different institutes in a high pressure cooker for 3 months and seeing what we could achieve in a really short time frame. And yeah, yes, for sure, I would want to collect the data that you ask about in the next series of experiments, if and when it happens, yes. But I can't give you an answer to that. It would be too speculative at the moment.
Okay. Our next question says, suggests that you have a look at the variations in line sources, fans, slope drifts, and basin drifts, and contour currents around the Bahamas.
Okay. Yeah.
That's from JJG Raymond.
Noted. Thank you.
And just a note as well from Lillian saying that the main author of Virginia Tech's paper is Jeff Culp.
I appreciate that input, but I can't, my English is not good enough to be able to spell that now, but I know which one it is. So yeah, if it can be put in the forum, that would be excellent. Cool.
I think Dominica has actually shared that in the chat, so that's great for everyone.
Fantastic, thank you.
So our last question is from Chengpeng, saying, great work, thanks Joris. Did the channel display a lateral migration trend during your experiment?
Well, yes, in a way. There was an exaggeration of the channel asymmetry and a shift of the levees, which indicates also an imbalance in the sedimentation on the levees, which I would say there is a channel migration. But I'm the first one to acknowledge that actually a new series of experiments should tweak the turbidity current so that we can have a whole series of experiments running over the same channel and really look at the longer term evolution of the channel to confirm this migration. Because at the moment, the turbidity current we use, once it becomes quite depositional, and we choose a rather depositional setting for the turbidity current, the channel will fill almost all the way up in only one experiment. So we couldn't do repeat runs. And I would want to do experiments with slightly less depositional turbidity currents and then repeat runs to really confirm that the stratigraphic migration direction of the channel, and that we can really call it that we can actually confirm that. So my answer is a cautious yes, but to answer this question, I have specific other experiments in mind with repeat runs that I would want to do to really answer your question convincingly.
Fantastic. Thank you so much, Joris. I think a lot of this has kind of highlighted how young this science is really, and how much more we have to discover, which I think is really exciting. So thank you so much for your insight. Well,
thank you very much for the invitation, and thanks everyone for being here. Even though I didn't see you, I'm really happy with the discussion that came out. So thanks very much for your input.
Brilliant. Well, we're almost at the point of close for the meeting then. I'll just tell you a little bit about what we've got on next week. So come along to next week's webinar. We've got a talk from Cedric John from Imperial College London, who's going to be talking to us about emerging technologies to improve quantitative interpretations of carbonate rock images, which sounds fantastic. And if you'd like to suggest a future speaker, you will find the form to do so on Seds Online, so please go ahead and do that. And in the meantime, come along to one of our 5 coffee breaks. There will be one in a time zone near you. Check out the website to find the coffee break time and place. All the information is available, so come along. And just to conclude, I think there is a lot to continue discussing perhaps on this subject. So please do use the forums. The thread is there and available, so go ahead and post things up there. And we look forward to seeing your comments. And with that, I'll thank you, Joris, and close the meeting. Thanks, Joris.